Welcome everybody to the seminar on computational geometry and robotics, this time jointly with a group from the Technion. I'm very happy to introduce Oren Salzman. Oren actually academically grew up in this seminar. He's now a faculty member at the computer science department in the Technion. And Oren will tell us about a problem that has gained a lot of popularity in recent years in robotics, in AI planning, and it even appeared in the computational geometry software challenge last year. Multi-agent pathfinding, new analysis, problem variants, and algorithms. Oren, please.
Thank you, Danny, for that introduction. So like Danny mentioned, I'm going to talk today about the problem of multi-agent pathfinding. This is a problem led by several students, or the research that we're doing is led by several students in the lab, and I'm just going to present their work and take a lot of credit for it. And intentionally, what I did when preparing this talk is try to provide some of the work that we've done that has already been published and is more, let's call it polished, but also present some of the work that is still under research to spark curiosity, to get feedback from the community, and share the research direction that we're taking from an algorithmic perspective, from more robotics perspective. We're building these days the capabilities to not only show these results in simulation, but also in hardware, and see the discrepancies between the very clean models that I'm going to discuss today and the mess that we have in the real world. So like Danny said, the problem of multi-agent pathfinding has gained a lot of popularity, specifically due to Kiva systems, and the way they revolutionized automatic warehouses. So if you'd go to a warehouse 15 years ago, it would be something like the warehouse that we see on the right, and people would walk 10, 20, sometimes even 30 kilometers a day in order to get packages. And this included both getting to a pod that was storing items and reaching into the shelf and extracting the specific parcel that you needed. And Kiva systems realized that the problem of reaching into a shelf is a really hard from a robotics perspective, but getting to a shelf is actually quite easy. And then they created the systems like we see on the left, where basically robots come and bring the shelves to people. And this was a huge success. Kiva Systems was bought by Amazon and turned into Amazon Robotics. And since then, there's been a huge interest, both from the academic community and the industry, on looking at automated warehouses and coordinating the motion of these different robots in warehouses. Now, 1 second. So we can model the problem that I just described as the following problem called multi-agent pathfinding. So here we're given some discretized graph with n vertices, and we have a set of k agents, each with its own start and go location. And we want to compute a path for these set of agents that is feasible, namely each robot goes from his designated start to go location. It's collision free, so the robots don't collide along vertices of edges of these of this graph. And we want to minimize some objectives. So we want to compute optimal or bounded suboptimal or high quality paths. Now in this very clean setting, we have agents that are points and they move in discrete time steps. So the time is discretized. We don't account for kinematics or dynamics of the system. And at each time step, each agent can move across an edge or wait along in the vertex that it's currently stationed at. Now, it's important to note that the problem gained a lot of interest because of Amazon warehouses, but it can be used to model many real-life domains, either aircraft towing, pipe routing, computer games, train coordination. Danny mentioned the software challenge in the recent sausage conference, not recent, I think 2 years ago or recent. You're muted, Danny. It doesn't matter, but there's been the same types of challenges a year before. So the same type of challenges was offered in different conference. The Flatland Challenge, this is the cool trains that we see on the right, was offered in the NeurIPS conference as an RL challenge, and it was designated for reinforcement learning based solutions. Surprisingly or not surprisingly, depending on where you're coming from, the type of algorithms that I'm going to describe today, not by our group, by a leading group from San Francisco, outperformed the RL approaches by orders of magnitudes. The details are they had to collect points within a span of 8 hours. The best RL team, what it managed to collect, the winner that used standard planning-based approach collected the same set of rewards within 2 hours, and since that time step continued to dramatically outperform the RL-based approaches. So this is a very active field, but we're going to stick with the warehouse as a motivating domain in this talk. So I can already tell you the end of the talk. And the take-home message is that we still don't understand a lot from a theoretic point of view about the MAPF problem. And we're just scratching the surface in terms of our analysis capabilities on the problem. And when we look at how to improve it, we're coming to ask, what is the right variant of the problem that we need to study after almost a decade of the community solving basically the same MAPF problem and looking at different algorithms that are by now very mature. So the way the talk is structured is I'm going to give some algorithmic background. Basically, I'm going to describe CBS, which is one of the core families of algorithms that is used in the field. And then I'm going to present a work by my student, Afil Golden, who gave new techniques for analyzing CBS and reduced the complexity analysis for its running time by several orders of magnitude. And I'm going to share the work that Afil has done. And then I'm going to present new formulation of the problem or extension of the basic MAPF problem that I just mentioned, and give flavors of the algorithms and the challenges that they have that allow to solve these problems. With that, I want to start, but I'd be happy to have any questions along the talk. If it's more of a discussion, it's nicer for me. So the multi-agent pathfinding problem. Let's start with the definition that we gave, that we have a graph with n vertices and k agents. We saw this slide. And typically, we said that we want to optimize some objective. When we're looking at time objectives, the natural criteria that we want to optimize is either the make span, namely we want to minimize the arrival time of the last agent, or the sum of cost, where we want to minimize the total time taken by all agents. In the first part of my talk, I'm going to concentrate on the make span, and I'm going to defer discussions to sum of cost to the second part of my talk. Most of the results that I'm going to discuss can be extended from make span to sum of cost, but it's easier and cleaner to analyze. Now, to understand the complexity, finding a solution or even checking if a solution exists can be done efficiently in polynomial time. But if we want to optimize the problem, then it's computationally hard and the problem is NP complete. And this is true both for the make span, the sum of cost objectives, for general graphs, and even for simple graphs that are subgraphs of an infinite grid. So in some sense, solving the problem optimally is hopeless. But we still need to solve these problems, and we need efficient algorithms in practice. So the first algorithm that I want to describe is conflict-based search. It was presented almost 7 years ago by a group from Ben-Gurion University. And the idea is that we don't need to account for the interaction between all agents in advance, but only do this on a need-to basis. So the algorithm works as follows. We're going to try and find the path for each agent individually, finding the optimal path while ignoring possible conflicts between agents. And then we're going to work iteratively to solve these conflicts in a best first search manner, and I'm going to visualize this. Now we can have two types of conflicts. Either two agents occupy the same vertex at the same time step. And in this visualization, we have these two nice dogs, and they come to the same vertex from different directions. And then there's a conflict. Nobody likes to see dogs fight. On the other hand, we can have two edge conflicts where the dogs come from opposite directions, and then they collide along the edge. So these are the two types of conflicts that we want to avoid. And the way CBS handles it is in a two-level algorithm. The high-level search maintains a so-called constraint tree, where it has a solution for each agent. These solutions may possibly be in conflict. And we have a set of constraints associated with each node in this constraint tree. Obviously, we start with the shortest path for each agent and an empty set of constraints. At each step, we detect some conflict between these paths, and this introduces constraints. Now, given these constraints, we can split the conflict tree node into two child nodes, and then use a low-level search to replan a path for each constrained agent in these child nodes. So let's visualize how this looks like. Let's say that we have this graph, and each dog wants to get to its bone, the green dog to the green bone, and the blue dog to the blue bone. And we start by planning a path for each dog. So we have an empty set of constraints. Can you guys see my mouse?
Yes.
Okay, great. So we have an empty set of constraints, and we have a solution whose cost is 3. That's the make span. And we see that there's a collision between the two agents or two dogs at vertex E at the second time step. And now we can split the tree. We can say either the blue agent can't be at vertex E at time step 2, or we can say that the green agent can't be at vertex E at time step 2. This corresponds to 2 new nodes, and we can see that we added this constraint that the blue agent can't be at E at time step 2. And now if we run our low-level planner, because the blue agent can't be at E at time step 2, it's forced to wait at C. The green agent can get there at time step 2, and we found a solution whose cost is 4. And this pretty straightforward algorithm, if you apply it, if you instantiate it in an intelligent way. So what is the heuristic according to which you resolve conflicts and choose the next node to expand, and how you can resolve conflicts, which conflicts do you want to choose first, then this can be a highly effective algorithm, and you can turn it from an optimal to a bounded suboptimal algorithm pretty straightforwardly. Surprisingly, the analysis of this algorithm, which is one of the algorithmic foundations of the field, was not studied. And Ophir Golden, who just finished his master's, came and try to tackle the very challenging task of providing better bounds and analysis techniques for this algorithm, with the hope of shedding some light on the whole hardness of the multi-agent pathfinding problem. So this is work by Phil Golden. We presented it last year's SOX. And I mentioned that CBS is one of the state-of-the-art, if not the state-of-the-art, MAPF optimal planner, and it can handle highly non-trivial instances in several minutes. But it's very surprisingly that even if you change something very small in the environment, it can create very long running times with no, at least we couldn't identify any clear or clean indication of what governs the hardness of the problem for CBS. So this is what I mentioned. And what we're trying to do is bridge the gap between CBS's favorable performance and the crude complexity analysis that it has and had. And the hope is that this will help to shed light on why the problem is hard and pinpoint which parameters govern the algorithms, the problem's computational complexity. So let's talk about the original analysis. And for that, we're going to have these parameters, and I'm going to have them all around the talk so we won't forget. N is going to be the number of vertices in the graph. K is going to be the number of agents. And C is going to be the solution's cost. And the algorithm's complexity is going to be governed by the number of nodes that exist in the constraint tree. And in the worst case, this is how the original analysis went, each agent needs to avoid every vertex except one at every time step in an optimal solution. So the maximum number of constraints that CBS can apply is an order of n times k times c. I remind you, n is the number of vertices, k is the number of agents, and c is the solution's cost. And since we can split each node, the branching factor is 2, the overall complexity or number of CT nodes that may be generated by CBS can be 2 to the power of n times k times c. Now, this is already astronomically large, and there's already some inaccuracy here that we only made the analysis for vertex constraints. And we didn't handle edge constraints that can also be applied by CBS. And we verified this historical oversight with the authors of the original analysis. And in Ophir's work, he addresses edge constraints, but for simplicity of exposition, I'm going to only account for vertex constraints, and in the rest of my talk, ignore edge constraints. But it's important to note that we have to account for them in the analysis. What Ophir did is present a new analysis framework using mathematical techniques from other domains, which was nice to import them, and to dramatically reduce the bound on the running time by several orders of magnitude. So to already spill the beans, using the techniques that Ophir presented, we can go from an exponential dependency on both n, k, and c to an exponential dependency on k and c, and take n, the number of graph vertices, to the base of the exponent. And if we look at common benchmarks and plug in values for n, k, and c, then the asymptotic upper bound gives us an improvement of an order of magnitude of 10 to the power of 1 million and more for standard, pretty simplistic benchmarks. Let's talk about the techniques that were presented in this work. So there's 2 orthogonal techniques One is to basically argue that we can't have each agent located at every vertex at every time step. If we think about it, when an agent starts to move and it's located at its start vertex, obviously it can't be too far away in the next time step and the following time step. And there's a data structure called an MDD where we can use this insight to give better bounds. That is presented in Ophir's paper, and I'm going to skip that. What I'm going to do is present a recurrence relationship that was identified. And this allows us to express the size as a function of the number of remaining constraints, and then to use different tools to bound this recurrence relationship. So this is what I'm going to mention. To do this, I want to introduce a slight variant of CBS, which is the one we analyzed. And for those of you who aren't familiar with CBS, I'm sure when I explained it, you may have raised an eyebrow, because the way I presented it, either the blue dog can't be at E at time 2, or the green can't be at E at time 2. But we can say something a bit more intelligent or careful. We can say that the blue agent can't be at E at time step 2, or the blue agent must be at E at time step 2. And this is called disjoint splitting. And when talking to the original authors of CBS, they say that this is the right way to present their algorithmic framework. So given this variant of CBS, we have negative constraints and positive constraints. And in each vertex of our constraint tree, we can define R to be the number of remaining negative constraints, and S to be the number of positive constraints necessary to guarantee a solution. And then we can have a function, T as a function of R and S, which bounds the complexity of CBS's high-level search. And we can bound this by saying there's a branch corresponding to the negative constraint, a branch corresponding to the positive constraint, and we need to add one which corresponds to the current node that we're analyzing. Let's look at each subfield. So we have this node, and we know that the remaining work that we need to do is bound by T, the function of R and S. If we apply a negative constraint, obviously the number of negative constraints needs to be reduced by 1, and the number of positive constraints doesn't change. If we look at the positive constraints, obviously the number of positive constraints needs to be reduced by 1. But if you do some careful analysis that I'm not going to do here, we can actually reduce the number of negative constraints by 2. So we have this recurrence relation, and the base is not that interesting. And the question is, how do we bound the size of this recurrence relation? Now, in our setting, R, the number of negative constraints, is K times N times C. This is exactly what the original CBS analysis did. And S, the number of positive constraints, can be K times C. Why? Because each agent, we can at most bound its location once on every vertex in the final solution. So what we want to actually bound is T, the function that we have, as a function of KNC and KC. And notice that we have KC in both parts of this recurrence relation. Now, in Ophir's work, he presented 2 techniques for bounding the recurrence relation. The first is kind of straightforward, using induction. And the second is using generating functions, which is a bit more interesting. For the induction, it's not that hard to show that we have order R to the power of S, which gives us a bound of KNC to the power of KC. And this is already interesting because we removed N from the exponent compared to the original bound of 2 to the power of NKC. But we wanted to get something a bit tighter. This I already mentioned. 1 second. And for that, we used a generating function. So this is a mathematical tool that has a lot of uses. One of its uses is to bound recurrence relation. If you're not familiar, the generating function of some sequence is the function f of x, such that the sequence elements are the coefficients of the series expansion of f of x. And once you have this generating function, there is non-trivial but standard machinery that we can use to get candidates for asymptotic estimates of the value of their recurrence. So when we have one variable, everything is pretty clean. And when we have two variables, things start to become a bit more messy. But using these techniques, we can get a bound of E times N, where E is Euler's constant, to the power of Kc. Now, we wanted to verify this empirically, so we took different values of S, which corresponds to K times C, the number of agents times the number of the length of the optimal solution. And we looked at the original bound and noticed that Y here is a logarithmic logarithm on the bound's value. And here, the x-axis is the graph size. And we took the first induction-based bound of K and C to the power of Kc, and we see that already we have a dramatic improvement. And then we looked at the bounds that we got from the recurrence relation, and we also plotted the actual values of the function for these different values of N and S. This is the red and the blue. So because the red and the blue overlap, we see that our bounds are tight. So that was encouraging that we didn't do any silly mistakes in our analysis. And we see the dramatic improvement when compared to the original analysis. As I mentioned, we took a bunch of standard benchmarks that are used in the communities and looked at the values of N, K, and C just to get a feel of how we behave. And obviously, we're mixing and matching oranges and apples because there's an asymptotic worst case analysis. And here we're looking at actual benchmarks. So these need to be taken with a huge grain of salt. But just to get a flavor, the ratio of improvement here is 2 to the power of 10, 100 million, which is very impressive. Just some comments to conclude this part of the talk on the analysis. I mentioned at the beginning, both in the original analysis and what I presented here, we are not accounting for edge constraints. Inofil's work, he does account for them. He also accounts for some of costs. In terms of extensions, as I mentioned, CBS, the way it's actually used is using bounded suboptimal variants that allow any approximation factor that the user wants, and extending this analysis to these types of variants is super interesting. And what motivated us at the beginning of this journey is to use the analysis to understand why MAPF is hard, or when MAPF is hard, and to use this to design new algorithms. And this is still something that we need to complete, and any suggestions from the community would be appreciated. With that, I want to move to new variants. Danny, I have till 5. How long do I have?
You have 1 hour, including time for questions.
I see. Okay, so I'm gonna give flavors of these different variants, and I'm gonna maybe skip some details just so you could get a feel of how we can extend either to simplify or to be more realistic the clean MAPF problem that I mentioned earlier. So this is work by Nir Greschler, who also just finished his master's and presented this work at MRS. with Danny, who was kind enough to send me the photo of them having fun in England without me. And what Neil tried to do in his work is go back to the original motivation. And in the original motivation, we wanted to pick items off of bins. And obviously, to do this, we would have to have dedicated robots that have different capabilities than the ones that can just transport items from one place to another. And in some sense, we're looking at a very general problem where we have a heterogeneous set of robots, each with different sets of abilities and restrictions, and we want them to work together. And we call this true cooperation. In some sense, in the multi-agent pathfinding, the only cooperation they do is not run into each other. And now we also want to account for how they transfer items from one robot who's able to pick items to a robot who's able to transport them. So let's look at this visualization. Here we have the red robot, which is able to pick items off of the shell. We have the blue robot, who's able to transport them, possibly much more faster than the red robot. And they need to meet at some point where the red robot can place the item on the blue robot, and then the blue robot can bring it to the packing station. And the extra complexity that we have in this problem is that we need to plan where and when the two agents meet in order to maximize our optimization criteria. I'm going to skip the original problem formulation. It's easier for comparison, but let's look at the problem formulation of Co-MAPF or cooperative multi-agent pathfinding. So here we have a set of agents, and we're going to subdivide them into two groups, what we call initiator and executor agents. And these are the red and blue agents that I mentioned earlier. Each one has its own start location, but notice that in contrast to the original MAPF, we don't have a goal location. What we do have is a set of cooperative tasks. And each task has a start location. Keep in mind the previous figure where we know the location of the parcel that we need to pick, and a goal location. And this task is assigned to a pair of agents. We also deal with task allocation, but that is beyond the scope of this talk. And to complete a task, the two agents that are assigned to this task need to compute a meeting, which is defined by a location and a time. So if we have this visualization, to complete a task, the red agent needs to go to the task's beginning. It needs to move to the computed meeting location at the designated meeting time. It's going to meet the blue agent there, and the blue agent is going to take the parcel and go to the goal. So let's see this in animation. So again, the two agents computed the meeting location, which is here depicted in pink. And this is the additional complexity that is the challenge that we had to deal with in this work. And we see that the blue agent can take the green parcel and bring it to the goal. So I'm rushing through this, but what Neil did in this work is present an extension to CBS called Cooperative Conflict-Based Search. And here he had to deal with CBS and add another level of search in the meeting space. So this systematically gives a partial ordering between possible meetings, and the algorithm systematically computes for each meeting place the best solution possible in a CBS-like manner. And to do this efficiently and effectively was the biggest challenge in this work. We had the algorithm Co-CBS is both complete and optimal. And for additional details, you can see Neil's paper. With that, I want to move to less polished work. but things that are exciting to us and that we're working on them at the moment. The first work that I want to mention is by my student, David, who's working on what he coined terraforming MAPF. So for those of you who are not familiar, terraforming is a term borrowed from the sci-fi community, and it describes the process of modifying an environment to make it better suit your needs. Specifically, earth shaping and modifying the atmosphere temperature to make it more Earth-like. And this is work where David came to me and was puzzled. In some sense, we have here in our original problem of MAPF, the way I explained it, a set of static obstacles. So let's look at this very simple toy example where the blue circle needs to get to the red square and the green circle needs to get to the green square, and they plan their paths, and the path intersects these two obstacles. They form bottlenecks that force the agents to either wait or look for costly detours. And here they move around the obstacles. But we know that in our approach, the whole motivation for using MAPF is so the agents can move the objects around. And if the obstacles are movable, why not use this additional flexibility to alleviate congestion? So if we know that these two agents intersect the obstacles, we can choose one of these obstacles and have it move out of the way because we know we have that capability, and then have the agents move through this newly opened corridor and get to their goals much faster. So I'm going to play this video a few times. Don't be daunted. This is a visualization of a warehouse where we have the objects, the obstacles in gray, and we have the colored agents moving around. And we ran a MAPF algorithm optimally. Here I'm presenting the sum of costs. So the sum of costs for the MAPF algorithm is around 1800. And the latency, which is the overall length taken by the agents beyond the shortest path that they each had to take. So the shortest path is kind of a lower bound on what they had to take, and the agents took an extra 37 steps. Using David's approach, which allows to create openings, as we saw here, this is a zoomed up part of the opening, we can get shorter sum of costs and even get a negative latency. So in some sense, the agents don't have to do their shortest path as designed when the scenario had static obstacles, but they can create shortcuts that get us negative latency. How do we do this?
Oren,
Yes.
where in your videos do we see the obstacles being moved around?
So here you can see this is why we have this zoomed up part. So you see here the obstacles, the robots, this is the gray obstacle that moved out of the way. And here we have the robots go through this opening. I'm going to have a few more videos and then it's going to be clear.
Okay.
And the idea, and I'm not going to go into too much details, is to extend CBS in order to allow the agents to collide with obstacles by treating them as what we call demi-agents. Now, each collision includes a constraint that compels either the agent or the obstacle to compute an alternative path. And then this is used by the algorithm to assign some moving agent that is then tasked with executing this alternative path, clearing the obstacle to create an opening. So the way we do it, or the way David's research was planned, is using two thrusts. In the first thrust, we assumed that the obstacles are self-propelled. They can move out of their way by moving themselves, and each so-called self-propelled obstacle wanted to stay in its original place. But if the algorithm found that it is better to move it out of its place, then move it back and account for this motion in order to create an opening, then the CBS variant move the obstacle. Then we use this algorithmic building block for David's second research graph, where we used these assignment of which obstacles we want to move and move them around using dedicated agents. So let's see how this looks. We have here these two all of the agents in the middle row that we identified that needs to be moved. And you'll see that once an agent goes under this obstacle, it's going to become red, and it's going to move the agent out of the way in order to create an opening. And you can see that the rest of the agents use these openings in order to avoid going around the obstacles like the green and the blue agents do. So let's watch this again one more time. And all of this is figured by the algorithm, which is called Terraforming CBS or TCBS automatically. So there's no hard coding of which obstacle do we need to move and when. Danny, is this clear?
Yeah.
Okay.
Thank you.
Okay, and I want to finish my talk by mentioning work done by Nitzan, where, again, if Neil's work created some additional complexity and David's work tried to create a variant that leverages the problem's unique characteristic, Nitzan is going down the same route and trying to understand how can we leverage experience in multi-agent pathfinding. I think I'm going to skip this cute animation where we had to identify, doing some Where's Waldo technique, and identify that agent 23, which you can never forget, moved from one slot to the other because we're a bit short on time. But in some sense, in many situations where we apply these algorithms, especially in the lifelong version, where we want to solve a series of MAPF queries, they're very simple. And the question we're coming to ask in this work is, how can we use information from one MAPF query to help solve and speed up a very, very similar query? And we don't need to run the same algorithm from scratch. And as I mentioned, the motivation is that usually we don't solve one MAPF problem, but we're given a stream of tasks. Not only that, we don't solve the complete MAPF problem, but we only solve it for a very short time horizon because we want to do it within a very with a very short time window. And then we're going to replan in a high frequency. So when you replan, you have these very, very similar queries. And this is true for warehouse environments, sortation centers, and so on and so forth. The approach that we take here is to adapt a different algorithm called priority-based search. And I think I want to leave time for questions. So I'm going to skip the technical details. If we'll have time later, then I'm going to go back to them. I just want to give a flavor of the results that we get. First of all, I want to say that identifying, so the key challenges that we have in this work, without going into the details, is how do we choose and define an experience? How do we build this experience over time using some database and use this database to detect queries that are very similar to what we have right now? And then how do we adapt and integrate this experience into MAPF solvers? And the way we do it, with skipping the technical details, is taking a less strict algorithm than CBS that is called PBS, and adding this experience. So just to give a flavor of the results, this is a sortation center that is a standard benchmark. And here we need the standard approach to solve this is to run a MAPF solver, specifically PBS, at a high frequency. And then we have these very similar queries. And what we did here is solved it once with PBS and then solved it twice using the experience obtained from the original solution. We call this XPBS, and then solve it again using PBS. So here we alternate between one PBS and two XPBS runs at every iteration. And what we can get here, and these are very preliminary results, I think I got them today at noon. So here we compare PBS and PBS followed by two XPBS. And we see that if we plot the number of agents as a function of the runtime taking to solve this, we get a slight improvement, which is not mind-blowing. What we do get is that within the same time step that is needed in order to make all this machinery work, we can increase the number of agents because we use the experience. And then when the original algorithm kind of hits a wall at 450 agents, and then PBS just fails, we can push this to 550 agents. And this is kind of very preliminary results. And by that, we can dramatically increase the throughput because we add more agents on a specific environment. That concludes the talk. I'd be happy to take any questions. I'd be happy to also dive a bit into the details on the difference between PBS and CBS and XPBS. But I think this is a good point to stop and see where the audience takes it.
Thank you very much, Oren. Questions? Oh, let me start with a question. One thing that we noticed in the computational geometry challenge of multi-agent pathfinding is at least one of the winning teams reported that the attempts to, did you try to apply your algorithms to the input of the challenge?
No, we haven't.
Because I just want to point out that one of the winning teams tried to apply, and CBS didn't perform well even on the simplest instances of the competition. It's true that the winning team ran high performance computing for a couple of weeks, but still CBS on those intensive, dense scenarios didn't perform comparably. I just want to make you aware of this and encourage you to look at these instances.
Yeah, I think that's a great point because there's a lot of the MAPF community has been highly motivated by these warehouse scenarios. And it may be the case that we're overfitting our algorithms and our benchmarks to these domains. And definitely the extensions that I talked about are only relevant for these types of problems. So we're in some sense looking at a narrower scope than the general MAPF problem. And it would be nice to see how, so in Nitzan's work that I mentioned, this is the general schema that we really believe is important, where we want to build an experience database and have some metric where we can detect similar queries. Notice that in the work that I presented, where we have this sortation center, in some sense, we don't need to build an experience database because we know, and we don't need a metric because we know for each query, what is the closest query. And when we look, so we have this general problem in mind. And when we look at the warehouse scenario, sometimes it's simpler and we need to be wary from overfitting our approach to these motivating scenarios.
Questions, don't be shy.
I have actually not a question, but perhaps it's more of a remark. So it's related to the contest, but it comes with a joke. I'll start with a joke. So this guy is rushing into the hospital. He's dying. The doctors are working on him. His relatives are waiting in the waiting room. and the doctors lose him. He passes away. The doctors come out and tell the relatives, we're terribly sorry, but we have tried all characters, CT, MRI, PCT, EEG. So why am I telling this? Why did I remember this joke? When we started with tackling the problem in the challenge, we also tried many techniques, and we did try. I think we did try CBS to some extent. We also tried the RRT and many more, and eventually, it's not that one worked better than the other. The only thing that worked for those large, at least large instances, was a variant of A star, and that's the only thing that worked actually. It worked both for the minimum distance and for the make span. And when I say a variant, I mean that we actually divided the problem into small groups between three, starting with 3 up to not more than 10 agents, I think. And we did run A star on those. Basically, A star is Dijkstra, but it boils down to solving, to using the extra with special handling of tie breaks. So we divided it into small groups of between 3 and 10 agents, and then we simply solved and added the constraint of the previous group. So let's say we had many groups of 3 agents. We started with the first 3. There were no other constraints except for the obstacles. And then for the next group, we used the obstacles and the paths of the first group, and so on. And that was
like
the
PBS.
only...
That's priority-based search, with
Okay.
each group being one agent, where priority-based search also searches over what is the right ordering that
So
you want to do.
So that's the next thing that I wanted to mention. The thing that we were able to play with after we realized that this is the only thing that works is the ordering of the groups and the partitioning into groups. And then we used some other things, but we did when we realized that this is the only thing that works, we didn't have much time left to actually try everything as we wanted, or at least I wish we had more time to try it. But it did work to some extent, and I think we used some sort of simulated annealing to try and play with the ordering, and we used a system of several servers to try everything out. So, okay.
Was that so? Is there a question or just a comment? Because
no, that's what I said. It's not a question. It's more of a comment. And
okay.
Thanks for actually giving it a title or a name. I mean, one of those acronyms. So as you said, it's, yes. It's... Yeah,
there's a zoo of algorithms. So I feel that here I'm representing a community, even though I'm not. Most of these works are not mine. I think what Ophir came, the first part of a talk, we set out with an ambitious goal of trying to identify the source of hardness for multi-agent pathfinding. And we tried to, our hope was to get some FPT, to get some parameterized complexity and understand what are the parameters that govern the problem in order to identify and design the best algorithm. And clearly the domains here are different from the domains in the sausage competition. But on the other hand, with the results that we saw from Flatland Challenge in URIPS, the best RL approach is embarrassingly weak compared to the machinery used. Again, they use some variant with PBS, and obviously you need to wrap it up into a system for it to work robustly and do some of the techniques that you described. So my first slide was, we still don't understand a lot about this problem. We have a bunch of tools. They work really well for some problems. We need to create better understanding better variants for specific cases, and definitely we need to understand why and when each one works. And I think that's my first slide, so I'm happy with this comment.
Any other question?
I just have a small question.
Yes, please.
Hi, Oren. I enjoyed the talk, and maybe it's a bit of a follow-up to your last comment. I'm just curious about the hardness of the problem, a bit outside of the realm of CBS. And when you said that you looked at FPT, can you comment on anything there? Did you look at warehouse instances, or what type of instances did you look at?
I can comment that we got no results. So we tried to identify. So I can't comment anything intelligent about it. That was the first thing that we tried, and then we narrowed the scope of a field's work and said, okay, let's focus on the analysis of one algorithm instead of analyzing the complexity of the problem. We did some work trying to benchmark fixed specific parameters for different warehouses, open scenarios, game-like environments, standard benchmarks that are out there. And there was no rhyme or reason that we could identify that could lead us to some good analysis. And that's why we narrowed the scope to analyzing CBS.